Hello everyone, now I am going to present and explain about the lab session that we have gone through for the past few weeks for subject electronic communication. My group consists of 3 members who are Nur Syuhada binti Amir, Nurul binti Muhammad Zulkifli, and Shurqiah Umamah binti Bahasan. There is a total of 3 labs for this subject. The first lab is about time division multiplexing, the second one is about analog to digital converter, and the last one is about digital to analog converter. So, I am going to explain about lab 1, time division multiplexing. There is 2 experiments in lab 1. For experiment 1, we need to generate the output signal waveform of triangle wave at output port TP1, then square wave at the output port TP2. And lastly, we need to generate output signal waveform of sinusoidal wave at the output port TP3. Firstly, for TP1, the figure shows the output signal generated from TP1 port. The signal showed the maximum amplitude and without distortion by adjusting the value of VR3 and VR1. Adjusting the clock knob will affect the period or frequency of the waveform generated. Next, for TP2, the figure shows the output signal generated from TP2 port. The signal showed the maximum amplitude and without distortion by adjusting the value of VR1. Adjusting the clock knob will affect the period or frequency of the waveform generated. Then, for TP3, the figure shows the output signal generated from TP3 port. The signal showed the maximum amplitude and without distortion by adjusting the value of VR2. Adjusting the clock knob will affect the period or frequency of the waveform generated. And now, for experiment 2, we need to generate an output signal at TP4 of triangle waveform at channel 1 and at TDM output at channel 2, and output signal at TP5 of square waveform at channel 1 and at TDM output at channel 2. And also, we need to generate an output signal at TP4 of sinusoidal waveform at channel 1 and TDM output at channel 2. Firstly, when connecting TP4 and TDM output, they will both form a waveform. Figure shows the output signal generated from TP4 port, the green wave, and TDM output, the yellow one. The TDM output signal showed a lot of distortion due to multiplexing. Since the multiplexing occurred in a short period of time, this causes the mixing of signals, thus resulting in distortion seen in the result. Next, when connecting TP5 and TDM output, a wave are formed. Figure shows the output signal generated from TP5 port, the green color, and the TDM output, the yellow one. The TDM output signal showed a lot of distortion due to multiplexing. Since the multiplexing occurred in a short period of time, this causes the mixing of signals, thus resulting in distortion seen in the result. Lastly, when connecting TP6 and TDM output, they will both form a waveform. Figure shows the output signal generated from TP4 port, the green one, and TDM output, yellow. Only for this TP6 signal, the square wave cannot be displayed due to slight misunderstanding of the port to be used. The actual port to be used is TP6, but in the procedure stated to use port TP4. Maybe this is one of the reasons the result is a bit different and square wave cannot be portrayed. There are a few questions that were asked in the discussion. Firstly, describe how the multiple signals transmit on the same transmission channel. Multiple signals are transmitted over the same transmission channel using the multiplexing technique. Multiplexing allows numerous signals to transmit in various time slots over the same channel. In a brief session over the channel, just one signal is allowed to send at a time. In particular, in TDM, overall transmission is divided based on the number of signals that must be carried across the shared link. Each broadcast source is assigned one or more time slots in each frame for signal transmission. The next question, explain the method of producing the sinusoidal waveform. One approach for producing a sinusoidal waveform from a DC source is utilize a Wien bridge oscillator. The basic component of the Wien bridge is a pair of RC networks, one of which is connected in series and the other in parallel. The op-amp is employed to generate a gain of 3, which compensates for the RC network's attenuation. The R2 component distinguishes the basic wind bridge architecture from that used inside the ETEK SES 3005. The classic wind bridge only has one resistor, but our board has two, one of which is a resistor with two diodes in opposite directions, linked in parallel, and the other is a variable resistor VR2 which can be changed by the VR2 knob. The next question is explain the method of producing the square waveform. There are many methods for generating square waves, but this lab will be focused on the op-amp stable multivibrator, which the CDC 4017 IC. The frequency of the square wave is determined by the resistor VR1 and the capacitor C1. The R1 and R6 resistor from a voltage divider setup that feeds a phase fraction of the output to the IC's non-inverting supply. Through VR1 is discharged by the capacitor and begins charging in a positive direction. This loop is repeated over time, and a square wave is swinging at the output of the op-amp between plus VCC and minus VCC is the result. And lastly, the question is about explain the method of producing the triangle waveform. The triangle waveform is formed on this board by feeding the square wave generator's output to the op-amp integrator. The R5 and VR1 control the integrator's gain, while the RB and VR3 control the square wave's bandwidth. As a result, the VR3 and VR1 knobs may be used to regulate the development of a triangle waveform. Due to a short circuit, the feedback loop is disregarded when a positive square wave peak is delivered to the integrator, causing currents to flow into the input resistor of VR1 and R5. Following that, the capacitor C1 begins to charge, increasing its impedance and therefore the gain. As a result, the amplitude of the ramp grows until the capacitor is fully charged. The capacitor quickly discharges as the negative square wave peak passes through the integrator, and it begins to charge in the other way. The output created will be a negative ramp since the condition is inverted from the positive peak. And that's all from me. I will pass the presentation to my other friends to explain about Lab 1, Lab 2 and Lab 3.
On the next part we discuss about Lab 2, which is analog to digital converter. The purpose of this lab is to understand the operation theory of analog to digital converter and implement the analog to digital converter by using ADC 0809. For the first task, we obtain the measured result of ADC 0809 single channel input, when the voltage is injected as the analog input to obtain the digital output, which have the ideal values and the experiment values. For voltage is equal to 0, the binary digit for ideal and experiment is all 0. For voltage is equal to 0.5, the binary digit for ideal is 0001, 1010, and we obtain the same result for the experiment values. For voltage is equal to 1, the ideal values is equal to 0011, 0011, and for the experiment values is differ, which is 0011, 0100. For the voltage is equal to 5, the binary value for both ideal values and experiment values is all 1. For the next experiment, the table shows the measured result of ADC 0809 multi-channel input. For this experiment, we need to modify the switch, which is SW3, SW2 and SW1. The input terminal and the voltage as the analog input, and the changes on the LED is recorded as the digital output. For the first situation, where SW3 and SW2 is connected to ground and SW1 is connected to positive 5 volt, the digital output is 1101, 1011. And the next situation where SW3 and SW2 is connected to positive 5 volt and SW1 is connected to ground, the digital output is 0010, 0101. Next, the method of analog to digital conversion. In theoretically, where the most ADCs take voltage inputs ranging from 0 to 10 volts, negative 5 volts to positive 5 volts, and create digital output in the form of a binary number. Technically, from the view of the block diagram, first we have sample where the analog sample at interval time. The sample frequency is important while converting the signal. For the second block, the whole sample amplitude until the net sample is obtained. The third block is quantization, where it converts continuous analog amplitude to discrete amplitude. It comprises discrete amplitude as well as time. The signal will be in digital form. And the last block is encoder, where it transfers the signal from digital to binary form. The purpose of SW1, SW2, and SW3 is to control the channel selection. And the adjustable errors of ADC 0809, where first, adjustable error is plus minus 1 LSB or 0.01953 volt and include full-scale error, offset error, nonlinearity error, and multiplexer error. Second, full-scale error, where it shows the offset error between the analog input and the full-scale analog input VREF in ADC when maximum value is reached. The third one is the offset error, where the difference between the center of the least significant code and the same code on an ideal ADC with the same number of bits. And the last one is nonlinearity error, where the discrepancy between a defined straight line of the sensor output curve across a specific pressure range.
My name is Nur Syuhada binti Amir, and in this video I will present Lab 3 Digital to Analog Converter. My lab members including Nurul binti Zulkifli and also Shurqiah and Umamah binti Bahasan. This lab consists of two objectives, which are the first one to understand the digital basic theory of digital to analog converter, two to understand the operation theory and characteristic of DAC 0800, and three to generate the unipolar and bipolar analog voltage by using DAC 0800. Moving on to the results of the experiment, mind that in this experiment we use ETEK ACS 3007 module. This lab session consists of two experiments, and the first experiment is DAC 0800 unipolar voltage output. Firstly, we calculate the step value using the formula Vmax over 2 power of n. Vmax is the output voltage, which is 5 voltage, and n is the number of bits. Referring to the digital inputs, which has 8 bits, so 2 power of 8, and we got 0.0195 volts. So to measure the I output, to measure the current output, we let J1 open circuit and measure the output current using digital multimeter. Then we remove the meter and let J1 be short circuit to measure the voltage output using digital multimeter. To calculate the theoretical values of I out and also V out, we use provided equations from the lab manual. Thus, based on the digital input from D7 to D0, we adjusted it to measure the I out and also the V out. Next is experiment 2, which is DAC 0800 bipolar voltage output. Firstly, we calculate the step value using the same equation with Vmax over 2 power of n, and we still got 0.0195 volts. Then, we use the provided equations in lab manual to calculate the value of the output current and also to calculate the V out output voltage too for the theoretical voltage. Then, according to the digital inputs, we adjusted D7 until D0 to measure the V out, I out, and also I bar out. As example, to measure the output voltage, J1 and J2 is short circuited, and J3 is open circuited. Meanwhile, to calculate the I out, J1 and J3 are open circuit and J2 is short circuit, and to measure the I bar out, J2 and J3 is open circuited and J1 is short circuited. Then the total current using the formula I out plus I bar out. Next is the discussions of both of the experiments. In experiment 2, if the digital input signal is 0110110, then what is the output voltage? So if from the experiment we got if the digital input is 011010110, the output voltage is negative 0.82 voltage. Then if the digital input is 0110110, the theoretical value of output voltage V out is, so we got the I reference equal to Vref over R1, and the I out equal to Vref over R1 times all the digital input divided by the number of bits. Then I write I reference equal to 1.0638 times 10 power of negative 3 ampere or 1.0638 milliamp. And the I outs, we got 4.4052 times 10 negative power of 4 ampere. So for the total I bar outs, we got 6.2328 times 10 times 10 power negative of negative 4 ampere, and V outs we got from the formula I out minus I bar out times R4, which we got negative 0.86 volt. So this is the output voltage if the digital input signal is 011011010. So the difference of experimental value and theoretical value is 0.04 volt. This happened due to error of voltage power supply not supplying exact 5 volt to the DAC 0800. Question 2. Explain the resolution and step size of DAC. Resolution or step size determines the minimum potential change in voltage or current for the DAC output signal. An 8-bit DAC that produces a maximum output voltage of 5 volts, for example, has a step size or resolution of 19.5 millivolt. The resolution is often expressed as a percentage value. The percent resolution for the 8-bit DAC is equal to, using formula 1 over 28 times 100% equal to 0.39%. Next, the n-bit DAC resolution or the step size using the formula V out over 2 power of n, where V out is the output voltage and n is the number of bits. Question number 3. Discuss the application examples of DAC in communication system and its functional operation. Firstly, we can find DAC in software radio. A DAC is used in a digital signal processor to convert a signal to analog for mixer circuit processing and then to the radio's power amplifier and transmitter. Next, DAC also can be found in data distribution system. Many industrial and manufacturing lines require numerous programmable voltage sources, which a bank of multiplexed DACs may provide. The use of DAC allows voltages to be altered dynamically during machine operation. Next, DAC also can be found in data acquisition system. An analog to digital converter digitizes the data to be calculated and send it to a processor, the ADC. In the data acquisition, a process control N will also be used, in which the processor passes input data to a DAC for a conversion to analog signals. DAC also used in video encoder. Video encoding is the act of processing a video signal and transferring digital signals to a number of DACs in order to generate analog video signals and maximize the output levels of various formats. As with video codecs, these ICs may have included DACs. Last but not least, DAC also can be found in audio amplifier. For example, for generating DC voltage gain with microcontroller commands, DACs are used. The DAC can also be integrated into an entire audio codec that contains features for signal processing. That's all from me. Thank you.